Hello, everyone. Welcome back to the Topos Institute Colloquium. Today, we're very happy to have Patrick Shafto talking to us about autoformalization and the future of math and science. So please, Patrick, whenever you're ready.
All right. Thanks very much for having me. Thanks for everyone joining. Um, as David mentioned, I'm going to talk about autoformalization and the future of math and science. Sort of subtext here is how far will we go and how fast. It'll be a somewhat less technical talk than I would often be giving, but um, I think it will address it will raise some questions that I hope are of interest to folks. And I should say that, I'm a professor at Rutgers in math and computer science. I'm also a program manager at DARPA. All of what I'm saying today is as my professor hat. That is to say, nobody has endorsed these comments today. So without further ado, I'd like to do a little bit of level setting to hopefully get folks on the same page. I don't know how much people are tracking the world of AI and math, but it's moving very quickly. So I'm going to give a slightly cartoon version of the ages of AI and math, um, which are meant to illustrate exactly how fast I think things are going. Um, so sort of starting out, like I would, there are many ways to start this, but like one landmark event for me was the first results coming out of DeepMind in knot theory. So this was work by Alex Davies with Jordy Williamson and others. So this was December 2021. This stands out in my memory, first of all, because it was a relatively high profile paper, also because I was at the Institute for Advanced Study in Princeton and um, interacted, the folks from DeepMind visited and talked with us at length about, about the approach and the results and so forth. Um, and it was the moment where it sort of became clear to me that there was the thing happening and the thing was going to be potentially important. Um, what also stood out to me about this is that it wasn't deeply about mathematics per se. Um, that is to say, the basic approach that they used was to translate a math problem into a familiar machine learning style problem and solve that. And so while very, very cool, didn't seem to deeply get at um, the sort of mathematics um, from an AI standpoint. And I should say that this sort of what I'll call the machine learning style of I think of as continuing to this day, which I think is sort of an interesting feature. That is to say that this work, which treated sort of knot theory as a kind of classification problem, um, was one approach, and more was sort of followed by a variety of work that I think of as being in sort of the same vein. In particular, FunLaw and function search, which turned into AlphaExplore, and continues to generate papers. I put up Francois Charton's Google Scholar page here just to sort of illustrate that I think he's one of the people that have been pursuing this and to interesting effect in general. And so I think this is a potentially very productive line of work. Um, but again, this is all just to say that, I think the age to me sort of dawned around the end of 2021. And it took a little while to move forward toward math in a more authentic way. And I'll put that date around January 2024. In particular, what I'm calling the IMO age, right? And so this is the paper highlighted here is Alpha Geometry by DeepMind. And it was, really focused on IMO level problems. And that rolled forward till this past summer, 2025. in which multiple teams, including a team from Google as well as DeepSeek, Harmonic, earned gold medals on the IMO, or the equivalent of gold medals on the IMO this past year. And so, this is not sort of state-of-the-art mathematics yet, but it's starting to engage with diversity of problems that are representative of different areas of math. And so a little bit more authentically considering mathematics. Roll forward now, just, another year essentially, or 2 years, I guess. The end of this past year, what I'll call the Erdos age, starting around the NeurIPS conference, so the beginning of December of 2025, multiple teams started announcing resolution of various Erdos problems. And so this includes harmonic as well as logical intelligence, and a few others have announced these kinds of successes, as well as people working with AI systems have been knocking down these problems. And so, these have the distinction of being proposed by a relatively well-known mathematician and being open in the literature, if not always the deepest and most profound problems in the field. Again, fast forward now just a couple of months. So we're up to this month, what I'll call the first proof age. This was just a few weeks ago. The multiple mathematicians got together and announced a contest in which they posed problems that didn't have solutions in the literature. So there were things that they had solved in the course of their own work, but had never published. And so these are distinguished in that, they're really fairly close to the frontier of mathematics at this point, right? These are very well respected mathematicians in general, posing problems that are effectively open and at the frontier. And so that's kind of where we are today. The full results of this haven't been announced yet. It's safe to say that some teams have gotten some solutions, but I think exactly like how many people participated and how successful they were, it remains a little bit open. And that brings us to, essentially today, right? And so what I want to, the exercise here was to point out that, in fact, this timeline doesn't go very far back and seems to be accelerating, right? Which is, I think, an indication that, there really is a fantastic amount of progress in this space in a very short amount of time. And so on the right side, I pose a variety of other questions that we haven't quite gotten to yet. So like, when are we going to start solving Fields medal style problems? Obviously, there's not a unified notion of what a Fields medal problem is. It's sort of a voted upon thing. But it sort of is representative of a caliber of problem. And then, of course, there's questions about Millennium Prize problems, which several teams are working on already. And then I'll sort of close with a question about going beyond mathematics itself toward science more generally. So what I'd like to ask is, given the history of what we've got in the past several years, what's it going to take to really take this sort of step forward, even to, first proof, but beyond, to really scale these results? And what I'd like to argue is that, what we've seen so far in terms of successes are largely what I'll call hammer and chisel type efforts. They're efforts that are not overly general and critically involve humans in various ways. So what I mean by this is that, in the machine learning age style, take the knot theory problem, there was an incredible amount of work to extract the knowledge from the AI system in order to write the paper, right? To sort of extract the insights from the AI model. And that was, just a very, very heavy lift. Similarly, the subsequent efforts of Alpha Explorer and Fun Search, they're quite excellent at generating examples that humans would never be able to sort of generate. But there's still sort of a last mile style of work of like figuring out what it all means in together. Similarly, if you look at the IMO stuff, there were by and large not backed by actually general approaches. There are a couple exceptions to this, but notably, they all leverage the fact that there's a judge to assess them at the end, and that, for example, DeepMind, in their gold medal winning efforts, did not use formal verification. And so, what I think it's going to take to get from where we are today to these bigger efforts is a more systematic approach in general. And so I'd like to just sort of contextualize that a little bit, if perhaps a little bit grandiosely, by sort of highlighting some where this hammer and chisel idea comes from. This is from McLarty's work. He's quoting Grothendieck in the middle here. And in particular, it's in this quote where Grothendieck describes his own work as sort of being like the rising sea, sort of seeing things, mathematical concepts from a relatively generic standpoint where there aren't a lot of exceptions, and sort of not necessarily doing things that are that appear totally transformative, but rather these long treatises that basically act like the rising sea, where a solution just falls out at the end. And so I think something similar is at play in what it's going to take in order to get from where we are today to these bigger problems, such as formalizing Fields medal level work or Millennium Prize problems. I can also speculate about timelines, but maybe I'll leave that to the end. So there is in principle a solution, and I've already alluded to it, right? Which is that there are formal verification languages, perhaps most prominently at the moment, Lean, backed by the MathLib effort. And these are interesting in that, it offers a generic view of mathematics. That is to say, in principle, it's all computer program. However, the state of the art as it stands right now is that it requires extensive human work at various points. The most important point is, mathematicians typically work in natural language, and that when you want code, a formally verified artifact, you need to manually translate it into code. And this requires a fantastic amount of effort in general. And that's just to get it into code. Of course, to get it into MathLib quality code is a much heavier lift still. And so there's a large amount of manual work over and above proving the result that's required at the moment. So this is an impediment to actually achieving these larger goals, in my opinion. There's a promising approach, and it's right there in the title of the talk here, that could make this much lighter work. And it's the problem of automatic formalization or autoformalization. I think there are a lot of reasons to believe in autoformalization as an important solution. They go beyond, whether we're going to solve formalized Fields medal winning problems. I think they actually address core problems in the field. In particular, the possibility of automatically reviewing papers, at least for correctness. There are many complications here, but the reviewing process is under great strain, and that strain is increasing with the advances in modern AI. And so I think there's a need for transformation on that front. I think there's also just the possibility of every mathematician working more efficiently and effectively. And this can be as simple as things that are already realizable today, such as automated literature review to discover results that maybe you hadn't read before. But of course, an AI system can ingest the entirety of the mathematics literature, at least the parts that are digitized. And so I think, even where we are today, there's a possibility of advancing mathematics. And of course, if it could also formalize and check intuitions for you or statements, that would greatly expedite work in terms of checking whether certain approaches were promising or not. I think there's also the possibility with a more complete formalization of the literature for new ways of doing mathematics. Here, what I'm thinking of is the links between papers, right? We reuse results standardly. Um, uh, and so there are sort of a variety of dependencies that exist across papers, but they're implicit in the literature for the most part, potentially cited, but the results themselves might, or the statements might be slightly different, tuned to your particular scenario, et cetera. And so there's this latent graph over the literature that is not yet explicit. And so this will be made explicit as we move toward formalization. And I think there are just really interesting styles of questions that one can ask when that's the case that we really can't right now. I think it can also broaden the possibilities of who can contribute to mathematics, right? The greatest pain point and the thing that we spend the most time training is the ability to prove things correct. And if any amount of that burden is lightened, it will enable a wider set of people to at least play with mathematical concepts and use them in some way in their own work or in building new mathematics. And I think that's a particularly exciting possibility. And of course, there's the possibility of providing access and training in pure mathematics to those who don't have access to pure mathematicians. Right? Because the core of formal verification in languages is the proof itself, the structure of proving. And so that could be leveraged in order to enable broader training possibilities. So I think there are loads and loads of reasons, these are just a subset, for why we should want automatic formalization individually and collectively as a field. But there's still some significant challenges that remain. So I'll identify four that I think are really interesting. The first is the formalization the same as the natural language statement? This is a surprisingly subtle problem. And one that is necessary if we're going to scale auto-formalization. Right? So if humans have to check every single translation, that will greatly reduce the scalability of the approach. The second is the formal-informal gap. That is, when we write papers, we don't include all the details. So any approach to auto-formalization would have to be able to fill in those details. The third is ensuring that the proof is actually a proof. Formalization is not a guarantee in any concrete sense, right? There are a variety of ways in which formalizations can fail. Some of them sort of boring, like making assumptions that you shouldn't have, to other things that are much more subtle. And so I think being able to automate checking of that is an important direction. And then finally, auto-informalization. So thinking of how to translate back out of formal languages into natural human language. Before I do that, before I talk about each of these challenges, I'd like to say a little bit about the problems of formalization themselves, and why informalization is important. So here's a relatively representative paper from the literature. This is a paper by Tim Gowers, Green, Manners, and Tao, called On a Conjecture of Martin. And it addresses the polynomial Freeman-Ruja conjecture. So I just copied the first couple pages so we can look at it, because I want to highlight that, there's structure to math papers, right? Here's a conjecture, here's a theorem, here's another theorem, here's a corollary. Entirely latent in this is that there's a dependency structure among among these statements. For this particular paper, the authors did a crowdsourced manual translation into Lean. Here is the result. Here, each of the rectangles represents a definition. Each of the ovals represents a proposition, or lemma or corollary, etc. Each of these ovals or rectangles has a natural language statement, and a formal translation into Lean. Importantly, of course, once it's in Lean, it also has to be, proven, if it's in, in order to be true, right? So each of these is an abstracted statement. And this here is a dependency graph. This is the work of multiple people. So on the order of a dozen or more people, depending on how you want to count the level of contribution. You can look at the GitHub yourself and try to assess what the right number is there over months. So the manual translation here is just intensive in terms of human effort. It's also sort of interesting to note that it is a crowdsourced effort, right? So we can already see that formalization does a thing that natural language math doesn't really support very easily, which is collaboration across many people, right? So I think Terry did most of the translation from natural language into a statement. And then you need to, of course, write up the proofs. But that was the part that was crowdsourced, right? And so many people contributed to this project, many more than would normally contribute to a math paper. Nevertheless, it's still just an incredible amount of manual work. Here is actually a picture of the GitHub repository, and you can see that there's, as promised, at least a dozen people who contributed. Really, totally, it's in the 30s of people who contributed anything. You can see that there's a lot of commits being made over time. Here it's on the order of around a year or a little more. We roll that out across just arXiv, for example. This is the plot of math papers on arXiv. We're talking roughly 22% of arXiv, at least as of 2022. Very, very large number of papers. If they require this amount of effort, formalization is not going to happen at scale. Fortunately, there's been a great deal of progress very, very recently toward auto-formalization. So this is basically the past year. And so I'll give one story on this front, which is from the prime number theorem and beyond project. So this was a project initiated by Terry Tao and Alex Kontorovich to crowdsource a formalization of the prime number theorem. And they broke it up into three levels of problem, the sort of what they called easy. I think they called it easy, medium, and hard, but basically three levels of the problem. And so here's the announcement from Mastodon, from Terry, announcing the project. And that was, I think, January 2024. And roughly a year and a half later, we have the announcement from Alex Kontorovich, which effectively declared victory. after achieving the formalization of the medium version of the problem. And so this was work by many, many people over the roughly year and a half, and they stopped at the medium version. Great achievement, really, really cool result. Um, but they seeing the amount of work that had gone in and the level of uh, commitment that would be required in order to achieve the strong version, they stopped. In particular, there were parts of complex analysis that had not yet been formalized that needed to be formalized in order to get to the strong result. So they stopped, and this was July 2025. 8 weeks later, a company called Math Inc. Announced semi automatic formalization of the remaining problem. So achieved the proof of the strong prime number theorem. Um, so this was semi-automatic because uh, there was one mathematician on the team, Jared Lichtman, who interacted with their auto-formalization agent called Gauss um, in order to do this completion. But I think it's safe to say that if Terry and Alex had thought that the project could have been completed in 8 weeks by even the team that they had, they probably would have continued and finished it. Right. And so it's quite remarkable that one person working together with an auto formalization and automatic proof agent were able to complete the project. And so again, akin to what happened in December of 2021, seeing this really brought to my attention the fact that this was actually happening. They had had a slightly they had had another result from this same team in June related to a relaxation of the ABC conjecture, but it was a much more manual effort required for that. So, sort of seeing this, I think, was an interesting uh, landmark for me, at least. Yeah.
Can I ask a question?
Sure. Yes. Go for it.
I mean, you would say that how much of this Math Inc. project depended on the stuff that they had done, that conservation, and I mean,
Oh,
it's presumably because it's mathematics, it builds on itself, right?
absolutely. Yes. No, no, they definitely built upon the previous results, right? So there was, yeah, yeah, I mean, the medium result was critical in achieving the strong result.
Right.
So the evidence here is really that Alex and Terry had stopped the project, and within 8 weeks, a single person had been able to complete it with the assistance of an
But
auto.
building on that, right?
But
Super.
yes, very much
Thank you.
building. So yeah, I'm speculating about how much work was necessary, right? But um, but there's still a lot of human engagement in this problem, right? Jared worked closely with the Gauss agent, checking the formalizations, making suggestions, manually elaborating parts of the proof as necessary, right? Like things like this. But again, this was last September, right? So very, very recently. Um, Along the same sort of timeline, there's a several important efforts in this direction, right? So we already mentioned Math Inc. Harmonic, of course, is another company in this space. So they had an auto formalization agent participate in the IMO and achieved gold. They also have an open API that you can use to ask for formalizations and proofs. So that's publicly available at this point. There's another company, Logical Intelligence, that was announced on a sort of similar timeline in 2025. I think most people have heard about Axiom also, and in particular, the company being announced and then Ken Ono joining. And so, that's, I think, a real endorsement from Ken to join one of these companies because he wanted to do more math. And so I think a really interesting development. So this is all sort of roughly on the timeline of 2025, so last year. There have also been a long series of workshops on math and AI. It's a little bit uneven in terms of whether they're interested in pure math necessarily, but there's certainly plenty of excitement in the world of machine learning and AI. This is from NeurIPS, so prominent AI conference. I'll put in a plug. I'm also running a program called the DARPA Exponentiating Mathematics program that will be kicking off next month, but has been in the works for, well, a couple of years now. So very exciting. A lot of energy in this space. So formalization is potentially a solution. There's a lot of momentum coming up over the past, even just the past year. I think there are a few real challenges that I think are important that we should be mindful of that we need to be able to address in order to make auto-formalization real. The first is the formalization the same? Right. And so the key question here is, right, you have whatever your natural language statement is, and then you have a statement in Lean. Of course, everything rides on whether these statements are equivalent to each other. And so if a human has to check each one of those, that's going to be a large impediment to having widespread auto-formalization. So the question is, how do we automate this process? Are there any ideas? And I should say that this is an open problem. I don't know of anyone who solved it sort of, at least publicly, claimed to have solved it. But there's an intuition about how you should do this, right? And it's the intuition we would use as mathematics, which is roughly, we would use as mathematicians, which is that you roughly want to sort of think about, well, what's a good definition? It's the kind of thing that proves the things you want to prove easily, right? And so like somehow, right, like you want the implications to have the right kind of structure. And we just have a translation problem where each of these statements has implications. At least in the case of existing literature, this is worked out in natural language. And so the question is, if you roll out the formalization of it, does it have the same implications? If it does not, then there was either an error in the proof or an error in the translation.
May I interrupt again? I'm
Yes,
sorry,
please.
but there is also another issue. There's two other issues that I wanted to point out. One of them is that you can do blueprints and the dependence between statements purely in natural language, and we have projects doing that. I have a recent January 26 preprint on that, and it's sensible to do it in natural language because then many mathematicians can check it, whereas people to check the formalization in Lean are slightly harder to, because the people who are doing it in Lean have to know both the Lean and the mathematics, right?
Yes, yes.
A
So
second
absolutely,
problem,
right. So when we structure papers, they're not broken out into like dependencies, clearly at least. And so Blueprint provides, that's what I've been showing is Lean blueprints
Patrick Massot's basic idea of doing blueprints. That's right. But you can do it differently. It's like you can do a generalized version of that. And that's what we are doing. But the second problem that we have that, it's not one of your challenges, but should be there, is this business of consistency of the mathematics that's being done, the mathematics that's formalized. Because, when the size of the code base gets to the size that Lean is at the moment and MathLib is at the moment, there's no guarantee that you're not somewhere, somehow, proving 0 = 1. And hence everything else falls. The beautiful edifice of mathematics would fall down. So I think, at least I would like to add it as a fifth challenge. I agree that all your 4 ones are good ones, but
So yeah, I'll touch upon I think what is related to that in the third one, but
Thank you.
I'd be open to breaking it out because there are multiple kind of sub problems in there. I just wanted to say for the formal informal alignment, right? We can check the implications. That only works for the existing literature, right? And so what do we do in the future? And this is one reason why I think informalization is important, right? Is that, of course, we want mathematicians to continue practicing mathematics. I don't think there's any necessary reason to port everyone over to Lean in order to do that. But also, right, like having two streams to align, I think, is an important regularization tool. The second challenge is
Sorry, can I ask a quick question?
Sure, yeah.
About that last slide. Maybe I missed. So this is not a guarantee that of alignment, right? It's just sort of a heuristic that if something has the same implications, then we probably is saying the same thing.
I think if you can roll it out far enough, where far enough is, potentially not a tractable, useful thing. But yeah, I think, to answer your question, yes, I think, I think many of the issues that I'm pointing to also have analogs in the existing math literature.
Well, okay. I could imagine like a statement that differs very slightly from the one that was stated informally, enough to have all the same implications, right? Like epsilon or epsilon over 3 or so, right? But it's still not exactly the same.
I see.
Yeah.
Yeah, I guess I would take the functionalist standpoint for that, that like if it's literally never different, then it isn't different.
But it's not literally. You're checking some finite number of consequences.
Yes,
Right?
that was my first
Okay,
point.
I just wanted to clarify. I'm sorry, I didn't
Yes.
mean to attack you.
Yeah, no. These are good questions, right? I think these are all things that we should care about because the details will matter. The second challenge here, I think, is filling in the gaps, right? So in a math paper, we leave things out, right? Just to sort of illustrate that concretely in the conjecture of Martin paper, there were only, again, this depends a little bit on how you count, but there were only roughly like 19 definitions, lemmas, propositions, theorems in the paper. In this oval that I'm highlighting here, there's 39. And some of this is breaking things up into pieces. So this is actually all, roughly speaking, theorem 1.3. So, some statements get broken out into more pieces, but lots of things are just not there that need to be filled in. Of course, we expect that a mathematician who is competent in the area, an expert, could fill in those details. But of course, there are also sort of potentially sources of problems, right? Things that we don't bother to prove that we probably should have can lead to mistakes. And so I think there's this interesting question of, having auto-formalization agents, it's not just enough to translate. They have to be able to fill in some cases, fairly non-trivial details. I think there's a solution here, again, these are all no guarantee kind of solutions, but like, vectors of progress, I guess. And it is to sort of think about the problem as a machine learning person would, right? Is how are we going to train these agents? Well, or what is the curriculum that gets us to the point where we can fill in non-trivial gaps in a paper? And the answer comes from sort of thinking about this graph, right? So this is just a directed graph. Each node here has a natural language statement, a formal statement, and proof. We can imagine omitting one or the other or pieces of each, right? And so we can think about this as a missing value prediction problem, very classic machine learning sort of perspective. So I have a natural language statement, I have to provide for you this, but we have it in the context of the graph, right? And so alluding back to my previous point, right? Like it has to be able to slot in there and not break the graph. And you can imagine scaling that down so that it's only pieces of the statement over here that are missing, or pieces of the statement over here that are missing, or scaling up, where you take not just the content of a node, but the existence of the node itself and remove it and ask to predict it, or the existence of subgraphs of the graph and ask to predict those. And you can see you can scale up from relatively small types of prediction problems like delete a character over here, all the way up to predict the entirety of this graph given, a few definitions in the theorem you want to prove, as a relatively sort of coherent, increasingly difficult problem. And so I think there's a good amount of progress possible here, just in sort of thinking through these kinds of problems. The third challenge is ensuring that the proof proves. I've taken a screenshot on the left here of a conversation that happened in the Zulip channel related to David Budden, who was claiming to be working on the Navier-Stokes problem, formalization, and there was a lot of back and forth around that. I don't want to highlight anyone in particular necessarily, but to point out that there's work that goes in, right? Like, is the proof actually a proof? And so Jason Root here is talking through that, some of the things were assumptions that, he was making assumptions that weren't valid, right? It couldn't have been a proof. And then worked with some folks to try to improve it, et cetera, right? There's sort of a back and forth. And so some of these things are automated in terms of checking that, you haven't, for example, just assumed the theorem that you want to prove to be true. And so there exists some tools along these lines, but they are heuristic. And so thinking through how do we check that a proof is indeed a proof and hasn't, had an end run around in some potentially indirect way is a non-trivial problem, right? In some sense, this is related to the idea of reward hacking in AI, potentially. And so there's one version of the problem that's that. On the right side, I highlight another version. This was a tweet by Elliot Glazer, who noted that it's possible to prove Fermat's last theorem in a way that avoided automated sort of checking, right? And in particular, if you follow him on social media, which I do recommend, has interesting discussions. He's highlighted sort of set theoretic considerations that can potentially complicate sort of the status of proofs. So I think there's a hard class of problems here that need to be solved. And this is related to the points that Valeria made earlier, I think. The last problem I'll highlight is auto-informalization, so translating from Lean back into natural language. I think there's a few reasons that we should think about this. It's potentially a little bit easier than the auto-formalization direction, at least if you're literally translating, because there's in general more details in the formalization than in the informalization. But there are also lots of things that we do about exposition in communication with our colleagues that aren't manifest in the formalization. So for example, we tend to front the interesting result, and that can be the theorem that's proven. It could be the method that's used as well, right? There are a variety of different things that we might be doing when writing a paper to communicate with experts in the field. And those aren't necessarily manifest in the formalization itself directly. And so I think there's some challenges here. And of course, we want informalization because we want mathematicians to be able to work in natural language math still. We don't want to require people to learn Lean. So these are 4 challenges. I'll try to wrap up fairly quickly. I think they're important. I think auto-formalization is important because it sort of treats the problem of mathematics as a problem of code and verification of code. And I think that's attractive in that it sort of is a general way of thinking about the problem of mathematics. I think it doing this at scale is going to be necessary in order to achieve the sort of bigger goals that we might have, such as formalization of or AI proving, say, Fields Medal level work or Millennium Prize level work, if only because it will be too difficult to keep track of all of the many attempts that happen and check them adequately, right? Like anyone can go to Gemini right now and ask for a proof of the Riemann hypothesis and like send it off to their favorite math faculty. And at some level, this problem has existed for a long time, right? Like people could always write a proof. It's just they were easier to identify the errors in when and they were at smaller scale than in this new AI age. I only have a few minutes left, but I don't have that much to say. I do want to highlight the possibility that, well, first of all, that we might make progress very, very quickly. I think it's possible that we could be seeing Fields Medal level work formalized maybe this year, given the rate of progress that we're seeing, right? This timeline is compressing. So that there's certainly, this is an ambitious timeline, but you might expect this kind of quality of result of previous Fields Medal level work auto-formalized this year. And then here's more speculation about what the timeline that we're looking at for Millennium Prize style work. And so in the next couple of years, potentially. So I think at least these are my guesses. I think, you know, the world's moving very, very quickly. And for that reason, I want to think about what lies beyond, right? Like why do we practice mathematics in some larger sense? And what would we do with an abundance of mathematics, right? The ability to do mathematics faster and more ambitiously. And I want to raise the possibility that we would tackle aspects of science and developing mathematical theories for domains that potentially don't even really legitimately have them yet. So, you know, I set up the early on, if the future of mathematics is automatic formalization, a bunch of positive things would result. I think all of the same statements work if you change it to science, right? Like there's really nothing special about mathematics here. That is to say, I think, you know, if we have automatic formalization of statements of mathematics, we've projected mathematics into code. And then science is much easier to do in a way that is verifiable, that other people can contribute to, and so on. So what do I mean by this? Well, we can pick a few example domains to try to articulate this idea a little bit more. First, and potentially easiest, is computer science, right? Programming. This is easiest because formal verification exists as a field. People have been doing this sort of thing manually for some time. I think there's and so, you know, at some level, this is uncontroversial, right? Like there's things that we're already doing. But what I'd like to roll that out toward is a larger scale effort, which is to say, much of computer science is not verified. What would it mean to verify computer science code at scale? And I think there's sort of two ways to sort of think about this problem, and they're a little bit analogous to what we've seen already. One is sort of thinking about AI systems that just formalize code and project it into machine code. And then there's a sort of opacity consideration. And then something that's more analogous to what we saw in mathematics, which is the idea of using natural language, in particular natural language math, as a declarative programming language to sort of bootstrap a more systematic treatment of computer software. And so, this is not, there are, of course, many efforts that have gone on to sort of think about formalization of aspects in theoretical computer science. And so, I think there's potential synergies there, but I think there's a sort of core idea of thinking about reusable abstractions for large-scale code that might be particularly useful and interesting here to explore.
Sorry to interrupt, Patrick, but just wanted to let you know you're breaking into your question time now.
Yep. So I'll just briefly say that I think quantum computing and information is another space where there's enough theory that in principle you could formalize things, but there are sort of hard questions. And so one potential target for formalization would be a famous result. Here's one. I won't say much about it, except that this is I think of interest in quantum computing and information theory to sort of think about the formalization challenges there. And then finally, I'll highlight that there are some domains of science, such as behavioral sciences, that barely have theory at all. And it would be really fantastic if this would provide a way to sort of think about inverting the development of theory, much like we think about estimation of parameters as an inverse problem in scientific model building. And of course, there are many other domains that sort of live in between. But I think there's interesting possibilities once large-scale formalization happens. So here's where we are. I think there's a very, very exciting next couple of years coming. Thanks.
Thank you, Patrick. Okay, we have time for questions. So I was just thinking, this isn't really a question, but a comment. NIST, basically, the National Institute of Standards and Technology has what is a kilogram, what is a second, and these are measurement devices that turn scientific units into activities that you can just do or something. And I was thinking to translate science into math, you could use those and kind of consider what nature does as the axiom system. So I'm going to do a thing, and when the kilogram comes out, that's just axiom. Just as a way to kind of formalize science. It seems like NIST is kind of giving us the translation from math to science-ish.
Mm-hmm. Yeah. I mean, measurement is sort of, measurement in theory, interplay. There's lots written about sort of that interplay, and NIST has really focused on that measurement point. And I think that would be the natural place to build theory from as well. Yeah.
Great. Let's go to Valeria.
Hello again. I kind of left my hand because I was wondering if there's other people who want to talk to, but I feel that we have a little bit of a problem here because your description of what was happening with this formalization of mathematics kind of did not talk about one thing that's very essential for machine learning, which is evaluation, right? And the thing is, we are kind of only doing things where we can evaluate because you're kind of insisting on things like IMO problems or Erdos problems, things that you can check that what is happening. But lots of mathematics is not about checking problems. Most of mathematics, in my opinion, is about building up theories and understanding the world. And for those things, it's very hard to get evaluation data. In particular, sorry, David, I'm coming up on what you're saying, but the fact is that we don't have standards of mathematical definitions. We don't even have a word net of mathematical definitions. And we all know, because we're all mathematicians, that we can define things in different ways. And if we define things in different ways, even if the concept is the same, we end up in serious trouble. So, that's why since 2021, with Brandon and some other people in the Topos Institute, I've been talking about this business of getting the basic vocabulary of mathematics done. Kind of, we have this project that was called MathFodar and are now called Network Mathematics, which is about setting up basic standards or basic definitions in mathematics, because without that, you can build all this wonderful stuff that the guys are doing, but you never know if there is a 0 = 1 somewhere on your code base, and you never know. I mean, and in mathematics, you can't just say, I don't care, he's 99.9999999% correct. If there is one wrong stuff, and there's plenty of wrong stuff when we're doing things with LLMs and even in code itself,
Mhm.
then it's not mathematics, right? It stops
Yeah.
being mathematics if there is this kind of error in the basis.
Yeah. No, you raise many good issues, right? I think I hinted at parts of, ways that evaluation could be addressed, right, by thinking about papers as the curriculum, existing literature as the curriculum, right? There's subtleties there because not all papers are correct. But I think,
Not
that's
enough.
also an exhaustible resource, right? Like we'll run out of those papers. And the questions then become like, what do we want from definitions as mathematicians rather than like, did it faithfully translate some previous result? So I think there's a lot of that kind of question. I think it's great that you're working on standard libraries. Of course, MathLib is an effort that sort of has some aspects of that as well, in terms of standardization. I think we do live with mathematics that's probably 99.99% correct, though, and like
But whenever we find that there is a mistake, we stop
yes,
and
yeah.
rewrite, right?
And I think one of the things that I find interesting about, thinking about these questions is that they really reflect the practice of mathematics in many cases, right? The challenges don't change actually. Um, and that's interesting to me.
Great. Thank you, Valeria. We have a question from Brendan and a question from Mike. So why don't we go to So Brendan asked a couple questions. Let's do Brendan real quick.
My questions are the same as his.
Okay, great.
Perfect. Shall somebody read them, or Pat, do you just want to respond? It's in the chat.
I can read them for you,
Oh, we'll read
Brendan,
it
if you
for the
want.
benefit of the live stream.
Yeah.
So question one, sort of similar to Valeria's too. Perhaps with the exception of the Fields Medal age, each of the ages you defined is about AI solving human-posed math problems. What about posing problems or even creating definitions? What is the potential role and timeline of AI in this part of mathematics?
Yeah, great question. So I think, posing conjectures, I'll start with, feels like a very tractable problem, right? And the reason why I say this is because, like, what is a good conjecture? Well, it's something that, if true or false, would have significant consequences, right? And so it's a subgraph, essentially, right? That has implications that matter to us. Uh, and so it doesn't have the feel of a totally different sort of problem. I think good definitions is a trickier issue in that, like, it's not totally explicit that we're not totally explicit about what we want from our definitions, right? Like I gave the cartoon version of like, well, it's the thing that makes all the things you want to say easy to say. And like, okay, fine, but like there's some, implied like fence around the things I want to say that I didn't quite say clearly, right? And so I think, conjectures and sort of new statements have a bit of that as well. So I think they're not totally free from that consideration, but I think definitions really highlight the human goals in a way that I think are interesting and hard.
Cool. Thanks. I'm interested actually, Mike, if you want to state your version of the second question.
Yeah, sure. Well, I would say it is uh what do you think the effect of AI and autoformalization will be on maybe innovation in foundations, particularly, right? Like, so Lean is a particular formal system.
Yeah.
And so if all mathematics is written in Lean now and all formalized in Lean, right, does that mean that other formal systems are not going to be as developed, or does it mean that is it going to be harder for these formal systems to work in some other formal for the auto formalizer to work in some other formal system, or is it going to be easier because the AI will be able to translate things back and forth for us more easily?
Yeah, I think this is a great question. My hope is that it will lead to much more research along these lines, right? Like much more freedom to play with different formalization systems at scale. That's my hope. That realizing that hope, of course, requires somehow answering the questions that you raise, like is translation doable / easy? Right? Are AI systems available? Because right, the thing that bottlenecks exploration of different kinds of formal systems is like how far can you get? Right? Like what is if you could check things at scale relatively quickly, it would be a really exciting domain to work in, right? Um, and so like having an empirical sense to that approach would be really quite cool. But I think there are hard problems that need to be addressed. Again, my hope is that like we have lots of languages that people explore and implementing different ideas.
Do you know of anyone working on that?
Translation, yeah, there are a few people, I don't know the names off the top of my head, that have been working on translation from Rock and Isabel and other languages into Lean, and potentially between those languages as well. Valeria, you have.
Well, I think we should probably stop the live stream and stuff here. But thanks everyone. Thanks again, Patrick. And anyone who wants to stay on and ask more questions is free to